In this example, we're going to use Newton's method to try to find the zeros of this function. So x squared minus 8. Now, we know that we could solve this analytically. We could say x squared minus 8 equals 0. X is going to be 2 times the square root of 2, which is somewhere around 2.8. But for this sake, we want to do a simple example using this method because it may be that we get to a point where it's not so simple to look at this and go, oh, well, clearly that's the answer. So we're going to fill out the table, and then what we're going to do is we're going to continue to do the method until the method or the inputs differ by less than 0.001. So that's a standard method. When you do this is you go, okay, I'm going to keep iterating until my inputs just don't change anymore. The reason you want to do this as opposed to your outputs is if you end up in some sort of cycle where your outputs are oscillating between the actual answer, you'll go in an infinite loop. But if you do it so that your inputs aren't changing much, generally speaking, you're going to get a better solution. So anyway, we start with an initial guess of 2 that's given to us. So what we have to do is we need to, since we're going to fill in the function and its derivative, let's go ahead and calculate the derivative of that function. So we just know that f prime is 2x. Simple enough. So if we're going to fill that out, then if I plug in 2 into this function, I get what? Negative 4. If I plug the number into f prime, though, I get positive 4. If I divide the function by its derivative, I get a negative 1. And if I take the input and subtract this, I get 3.0. Why is that useful? Well, that's useful because the value in this box goes into this box. So when I plug that in here, I get a 1. When I plug it in here, I get a 6. When I take the when I divide this by that, I get 1/6. And when I subtract that from 3.0, I get something like that. Now, if I were to continue this method on and take 2.833 and run it through all of this, what I would eventually get to is something that looks like this. 2.8284. And that's going to actually happen in the 4th iteration. So you're going to end up with one more iteration where this is your starting value, and then it's going to converge to that value. So this happens at n equals 4. And the key is you just got to keep plugging in. Now be careful. In an ideal world, you would do everything fractionally because you're not going to have precision problems. That's a big issue when doing numerical solutions is where do you round off, and does that round off cause error? But in this particular case, you're gonna get there within 4, and this is a very generous convergence condition. If that was like, instead of 2 zeros here, if it was like 12 zeros there, you'd have to be a lot more concerned about your power of your calculator or computer to not have round off error.